Hi, I'm Chris Maidment. Nice to be talking to you all. Today, I'm going to be talking about embedding power and really how to ensure a long and reliable operation of those power supplies. So first of all, just a little bit about myself. I'm the head of product management and technical marketing for TDK-Lambda and Maya. I'd like to say thank you all for taking the time out of your day to attend this webinar. I've worked in the electronics industry for over 30 years, and I would say I've been very lucky in my career as I've worked with a TDK company now for over 26 of those years. And I've been supporting applications such as phone RF front ends, right way through to 10 megawatt offshore wind turbines. Before I dive into embedding power, I'd also like to briefly introduce you to TDK and also TDK-Lambda. Okay, so TDK-Lambda, or TDK, was established in 1935 following the invention of ferrite cores, a technology that is still used today 100 years later. Innovations in magnetic tape, also multi-layer chip inductors, and also hard disk drives has followed. Through the years, TDK has grown significantly, both organically and by diversification. This included Lambda power supplies in 2005, and Epcos, my previous company, was acquired in 2008, and this continues today as well. Moving on, just very quickly, this is an overview of TDK-Lambda's product portfolio. As you can see, we produce power supplies from PCB mount DC-DC point of load converters, embedded AC-DC, and also DC-DC converters, right the way through to sophisticated programmable power supplies. In total, TDK-Lambda has in excess of 70 years of designing and manufacturing reliable power supplies. Therefore, if you have any questions, then there is a good chance that we've come across it before. Okay, so let's discuss embedding power. What do I mean by embedding power? In this instance, it is the integration of one or more assembled power supplies within an application's system enclosure or housing. This could be as simple as a small convection cooled power supply for a patient monitoring system, as you can see, or it could also be a multiple redundant power supply. I think something's there we go. So I suddenly jumped out there. So it could be a multiple redundant power architecture to ensure that critical loads are sustained, even with the loss of one or more of those supporting power supplies, or a sophisticated combination of programmable power supplies within an automated test equipment to evaluate maybe avionics or automotive systems. Embedded power systems can be found in many applications such as medical, infrastructure, renewables, robotics, transport, broadcast, and also others. Okay, moving on to the next slide, just bear with me. Okay, so first I should say that ensuring reliable operation of the power supply and therefore the system is dependent upon many variables. In fact, probably too many to cover in just 30 minutes. Here's a summary of those variables. You'll notice that I've highlighted 3 of the electrical variables in red. The selection of these parameters will directly contribute to the heat generated by the power supply. The parameters highlighted at orange will have an effect on how much of the heat from the power supply and the other system elements will be contained or removed from the system enclosure. The items are highlighted in green are parameters that the system architect will need to specify and evaluate as part of their thermal trials. And finally, the safety and certification requirements will be determined by the application the power supply is actually intended. So why have I highlighted parameters that are specifically related to heat? This is because the long-term reliability of an AC/DC power supply is very dependent upon the surrounding ambient temperature and the effectiveness of the cooling of the product. Power supplies use electrolytic capacitors, and their lifetime will be reduced in proportion to their temperature. A rule of thumb is for every 10 degrees C rise in temperature, their life is actually halved. Just a rise of 20 degrees C will result in the capacitor life being reduced by 75%. It is therefore essential to consider the heat generated and the heat management from the very beginning of the design process, as it will have a direct benefit to the system reliability. So the obvious question is, why do modern switch mode power supplies still use aluminium electrolytic capacitors? Well, the simple answer is they offer the power supply designer a number of advantages. There's high capacitance in a very small space. In addition, their rated voltages can support rectified AC mains. And when those two parameters are combined, this means they have a very high energy storage capability. You may remember the equation energy stored is half CV squared. This is half of capacitance times by the voltage squared. This energy store is critical, as I will explain shortly. In addition, they are relatively low cost, and as importantly, they have a very predictable lifetime behavior. Where are aluminium capacitors used? Well, power supplies use electrolytic capacitors for both energy storage and filtering. The high voltage bulk capacitance is specified to withstand short dips or loss of the AC source for a number of milliseconds without loss of the DC output. The large energy store that the aluminium capacitor provides directly relates to the power supply's hold-up time. Low voltage capacitors are used in the output filter section to reduce high frequency ripple and also the noise output transients caused by sudden changes in the load. Other aluminium electrolytic capacitors may be used in the control and also in the housekeeping circuits. I should say, degradation of any one of these capacitors may severely compromise the power supply's performance in the field. Therefore, it is really important to measure the temperature of all the capacitors within the power supply whilst in the system enclosure. I've shown where the capacitors are used electrically. However, let's identify them in practice. The first capacitor you can see is the bulk capacitance. It is easily identifiable as it will be physically large, and their voltage ratings will be in the order of hundreds of volts. The second capacitor is the output capacitors. These are much smaller. Their voltage rating will be above the output voltage of the power supply. For instance, for a 24 volt output, they'll be rated to around about 35 volts. Finally, this is a small surface mount aluminium capacitor used for housekeeping circuitry. As mentioned, early life failure of any of these capacitors due to high ambient operating temperature could result in the shutdown of the power supply, and therefore the system that it's actually supporting. So how do you measure the capacitor temperatures? Typically, during the thermal trials, engineers will be monitoring the operating temperatures of the aluminium capacitors by attaching K-type thermocouples directly to the capacitor body. If you can attach the thermocouples to the base of the capacitor, which is actually the top of the capacitor viewed here, that's a little silver disc you can see. This typically has a mechanical and therefore a thermal connection to the capacitor's cathode foil inside the capacitor body. It will take a little while for the temperatures to stabilize, anywhere between 2 to 3 hours. Once you've measured the temperatures, you can then compare them to the ECAP lifetime curves we publish in our application note. Now, the resulting worst lifetime will then represent the minimum lifetime of the power supply, which will, of course, will also be the end of the system life or the maximum service interval to replace the power supply within the system. Let's have a look at a typical ECAP lifetime curve. In this case, for our product, the CUS400M. CUS 400M is a 400 watt power supply with a single output. You can see a number of different colored curves, and this relates to the individual capacitors. You can see the map on the right hand side from the CUS 400M handbook. The capacitor that has the lowest lifetime is C15, the blue curve. In the example that I'm showing, you can see at 75 degrees C, the intersection to the blue curve indicates a 5-year lifetime. All the other capacitor measurements indicate greater than 5 years. Therefore, it is C15 we need to focus on. In other words, if you run this power supply for 24 hours, 7 days a week, and C15 remains at 75 degrees C, then you should get a minimum of 5 years of operation. If you can ensure cooling of the power supply to reduce the C15 to, say, 65 degrees C, then your lifetime would double to a minimum of 10 years. Of course, this is assuming continuous operation. If the power supply is only operational for, say, 6 hours a day, then your actual lifetime estimate can be quadrupled. So how can a power supply be cooled? In general, there are 3 ways to cool a power supply. There's natural convection, forced air, and conduction. And I include water cooling in conduction cooling. Each one has their advantages and disadvantages. Your selection as a system integrator will depend heavily on the intended application. Let's first have a look at natural convection. This is where there's no external airflow present, but air currents are allowed to circulate freely around and through the power supply. Restricting that airflow just by 0.3 meters per second with external components or an enclosure will result in much higher component temperatures and therefore a shorter life. In this image, you can see a typical open frame construction. An open frame construction allows heat to radiate away more easily. It has the lowest cost, but unless restricted, operators and service personnel will have access to any live high voltage components. Cooling by natural convection is typically used in applications where there is a reasonable amount of space to allow natural convection currents to flow. It has the advantage of operating silently. This makes it ideal for applications where annoying fan noise cannot be tolerated. A typical example could be, say, medical and office environments where too much noise can be disturbing to patients or employees. In both applications, the operating environments are generally not extreme and are typically temperature controlled, so natural convection is possible. Of course, natural convection is not exclusive to medical and office applications. It is also desirable in industrial applications where you do not want to draw in airborne contaminants that could damage or short out the power supply. However, as mentioned, if you're implementing convection cooling, any restrictions in the convection current caused by surrounding equipment can cause internal localized heating and reduction in the operating life. Even the mounting orientation of the power supply can cause internal localized heating and reduction in the operating life. As we have seen in a power supply mounted in a horizontal plane, it radiates heat vertically away from the power supply. If the power supply is rotated onto its long edge, the heat must travel through the power supply, therefore increasing the temperature of some components. If the same power supply is placed on its short edge, then you can see the magnetics are heating the capacitors. Therefore, TDK-Lambda will give you the documented guidance on what performance you can expect from various mounting orientations of the power supply. The exposed open frame construction is something's gone right. Here we go. Okay, the exposed open frame construction is also not ideal for some applications, as there is little protection for the operator or the service technician against electrical shock. Therefore, manufacturers of both U-channel and full enclosure options for open frame power supplies. Of course, this does mean that the cost will increase slightly, but may involve some thermal derating. The exposed open frame construction is also not ideal for EMI radiation. However, by adding an enclosure as a shield, the suppression of the EMI emissions can also be improved. I think at this point it'd be good to make a quick detour, just to discuss in a little more detail the topic of EMI. In this slide, I'm showing two power supplies. The first is a class 1 and the second is a class 2. Class 1 has an earth available. However, for class 2, it means it should be possible for it to be operated without an earth. Class 2 power supplies are particularly important for medical applications where they require low leakage currents to ensure patient and also operator safety. Leakage current is a current that flows from mains to ground. In addition, medical equipment also has to ensure emissions are below limits set by EN 55011-B. However, this is quite a challenge to achieve both. Allow me to explain. In class 1, the power supply's EMI filter can use the earth to direct the EMI emissions via a Y capacitor to ground. This means for class 2, where we have no earth, we cannot use this method to reduce the emissions. Therefore, our designers consider countermeasures to mitigate EMI at every stage of the power supply design. I do not want to brag, but TDK-Lambda has a full EMC and also DVT facility in our power supply design locations, and therefore we are able to evaluate EMI performance throughout the whole design process. Let's go back to our thermal discussion. As we have seen, adding a U-channel with a top cover can improve the EMI and reduces the risk of accidental shock. However, you also have to consider the possibility of derating the output power. This is because the metal shield can restrict the natural airflow. Therefore, you will need to refer to the manufacturer's derating curves. I've given an example taken from the CUS150M datasheet. This power supply can deliver 150 watts when air-cooled by either a system fan or an integrated fan option. But let's look at the convection rating curves, in this case, the blue line. As you can see by the red dotted line, at 50 degrees C ambient, the CUS150 will be able to deliver 100 watts to the load. Now, let's have a quick look at the derating curve for the same power supply fitted with a U-channel or a U-channel with a top cover. Again, this is represented by the blue curve. The solid blue line is a power supply fitted with the U-channel, and the dashed blue line is a power supply fitted with the U-channel and the top cover. As you can see, by adding the U-channel, you can actually increase the power rating, in this case by 20% to 120 watts. This is because the heat generating power semiconductors, like the switching MOSFETs, can be thermally connected to the metal U-channel case. Heat can then be conducted into the power supply chassis. The enclosure also has a larger surface area that we can now use to dissipate more heat to the surrounding environment. If we now add the top cover, the power supply still achieves a 10 watt higher power rating than the open frame unit. However, compared to the power supply fitted with just the U-channel, the power rating is 10 watts lower. This is because the top cover can restrict the natural convection currents. It is worth noting that TDK-Lambda top covers have hexagonal holes, not circular. Why? Well, hexagonal holes can be placed much closer together than a circular hole, and this means a cover made of hexagonal holes will allow convection currents to pass more easily than a cover made from circular holes. You can be assured that our engineers leave no stone left unturned to maximize the performance of a TDK-Lambda power supply. What if your system cannot use a convection-cooled power supply? Maybe it runs too hot due to lack of space, or ventilation is limited. Maybe you need more power than a convection-cooled power supply can deliver. The next solution is to consider forced air cooling by either mounting a fan to the power supply to aid heat removal, or installing fans in the cabinet to direct air around the various system elements, including the power supply. Cooling by forced air is typically used in applications where space is limited within the equipment, power demand is high, and the additional noise can be tolerated. In addition, operating ambient or altitudes may be at the higher end of the power supply specification. A typical example are servers where high-speed fans are used to cool equipment in racks. In this case, they take high power, but as the rooms are not manned, higher audible noise is acceptable. A lot of industrial applications, due to high power requirements will also require fan cooling. However, to prevent ingress of harmful contaminants, air filters are often placed over inlets and also outlet vents. Let's look into a bit more detail on forced air cooling. The basic principle is if you increase the volume of air passing through the power supply, you can then remove more heat, thereby extending the power supply's life, and also achieving higher power densities compared to convection-cooled power supplies. As with convection-cooled power supplies, it is essential that adequate space is given to allow unrestricted flow of air exiting the power supply. If not, hot air flows could re-enter the power supply, causing additional heating. It is not only the amount of air being delivered to the power supply that is important, but also the source temperature of that air. If the power supply is drawing air from a hotspot within the system enclosure, or maybe another system element is directing its exhaust directly to the power supply fan, this would therefore result in higher temperatures, and as we discussed, will also reduce the power supply life. So, which is the best direction to blow the air through the selected power supply? So this diagram shows cool air being blown into the power supply from the rear and exiting from the front. Cool air is drawn across the fan bearings, which is good for the fan's lifetime. Also, fast-moving air creates back pressures that can be directed at hot areas like the magnetics. However, in this direction, the output capacitors may run hotter. Also, more contamination may be drawn into the power supply due to the faster airflow. If we reverse the air direction, in this case, the diagram is showing a cool air being drawn into the power supply through the front of the power supply and exiting through the fan at the rear. The cool air is drawn in from the front over the output capacitors. This keeps these components cool, and their lifetime is actually improved. As indicated by the size of the arrows, the speed of the air entering the power supply is lower than the exit speed. This is because the cross-section area of the rear air exit is half that of the air inlet at the front of the power supply. The resulting lower speed of the air entering the power supply from the front of the power supply has the advantage that it's less likely to draw in outside contaminants like dust and dirt, which could also impact the product lifetime. However, the input capacitors will receive warmer air. As the input capacitors generally have a shorter life than the output capacitors, it's better to keep these the coolest. The higher speed airflow cannot also be easily directed at hot items like magnetics. So this is also a disadvantage. Hot air is also drawn across the fan bearings, which could affect fan life. The higher the temperature, the faster the bearings will wear due to loss of lubricant. If the fan speed is controlled according to ambient temperature, then this could also be mitigated. Also, for this reverse airflow, derating is likely to apply. Let's quickly go back to the CUS 150 example we used for convection cooling. You may remember that we could achieve 100 watts at 50 degrees C with the open frame unit with convection cooling, 110 watts with a U channel, and 120 watts for the U channel option. Again, There's no change to the electronics, but by adding fan cooling, we can actually achieve 150 watts at 50 degrees C. That's a 50% increase on the open frame convection cooled example. It is worth noting that the fan is limited to 70 degrees C due to the UL approval rating. Of course, we can also cool the power supply by using an external fan within your system. In this case, the curves are valid for a minimum airspeed of 1 meter per second. If your system cannot use forced air cooling due to noise or no access to ventilation, what are the other options? Conduction cooling is another solution manufacturers, including TDK-Lambda, actually offer. There are typically two options offered depending on the manufacturer. So for the first, it is simply to add a base plate to the power supply, allowing thermal transfer from the power supply to the system enclosure. The second is to add a U-channel enclosure, again allowing heat from the circuit board to be distributed to the system enclosure. Conduction cooling is ideal for applications where low or no audible noise can be tolerated, or there are no vents or fans allowed in the system. This may include medical devices. Certain noise frequencies from a fan can be irritating or tiring to a patient. For outdoor or sealed enclosure applications, waste heat can be conducted away from the power supply to the exterior surface, which often are thin for better heat extraction. The conduction cooling method is also used with water and also Peltier cooled systems. As previously mentioned, the power semiconductors on products like the CUS series are surface mounted and are attached to the underside of the printed circuit board. A number of companies manufacture flexible gap fillers with a high thermal conductivity and a low thermal resistance. When these are fitted between the underside mounted heat, when they're fitted on the underside, heat can then be transferred from the hot semiconductors to the metal chassis and then into the system enclosure. Again, using our CUS 150 example, we could achieve up to 120 watts with pure convection cooling. With fan cooling, we could actually achieve 150 watts. So what could we obtain with conduction cooling? If we now look at the green curve, you can see that by adding a cold plate to the CUS 150 with a U channel, we can actually achieve 150 watts at 50 degrees C. Again, a 50% increase on the original open frame convection unit. As with the convection cooling, the top cover can hinder the thermal currents. Therefore, with a cover fitted, the power output needs to be reduced to 137 watts. Of course, I anticipate the question, how cold is a cold plate? Well, the above curves are based on the cold plate being 6 degrees C below the ambient temperature. So we have now seen that there are various cooling options for embedding a power supply. Selecting the right one will avoid your system performance being compromised commercially or technically. Well, this brings my webinar session to an end. I'd like you to take two takeaways from this presentation. The first, it is essential that thermal trials for power supplies are conducted within the end equipment under actual operating conditions. With this information, the right power supply can be selected for a long and also reliable lifetime. And secondly, TDK-Lambda has more than 7 decades of expertise designing and also manufacturing innovative and reliable power supplies. We're here to help. We're here to help you find not just the solution, but the right solution. So I'd like to thank you all for your time today, and also joining this webinar. And if there's any questions, then I'm happy to accept those now. Okay, it looks like there's no questions, so obviously you're all very happy. So so I wish you all the best, and hopefully you'll enjoy the next session as well. So thanks very much.